Okay, let us start with our discussion on this stress and strain measures. So, the last lecture was on material properties, and we have seen that the material properties, they comes from some measurement. Now, when there is a measurement, of course, how the measurement is carried out, that is important. So, by changing some other measurement techniques, the properties which I have obtained earlier, that might change. That is what we are going to observe now, what are the type of measures, and we will be discussing true stress and true strain, both as such, because our observation comes from some material testing where we get both stress and strain, both the values we get from there. So, you see, if you link or click here, you will get to this particular slide, okay, and we will be discussing this through our downloaded file here. So, this is is the document. Let us focus on that. This is the topic. So, up to this point, we have discussed analysis of stress, analysis of strain. Now, we will go into the stress strain relation, which is generalized Hooke's law. We have just talked about that, we will establish it. Before that, we have measured material properties, and in that connection we are going to discuss about other type of measures. Okay. This is some material properties we have seen in earlier discussion. This is how we measure the stresses and strains, and what we have used so far is this particular measure, which is engineering stress by engineering strain. So, these measures, they are carried out with respect to initial gauge diameter and initial gauge length. That we have seen that there are 2 points on this specimen. Okay. The distance between them before deformation is known as gauge length, this diameter known as gauge diameter. But if we go on measuring, okay, the change in length at each stage of loading, and if we go on measuring the diameter at each stage of loading, there would be some change. Okay. So, that way our definition of stress can be the magnitude of force divided by the then cross sectional area. That would be another stress measure. So, that is known as a true stress measure. And then what we can do, say at each point of loading, if we measure the change in length and we go on calculating this strain, the instantaneous value of strain, that means taking the previous value as the original length, and then upon an increment of load, what is the change in length, and we calculate the strain at that point. And if we go on adding this strain, we will get another strain value. So, that way what we get is known as a true strain. Now, you see this particular diagram we have seen earlier. This is based on the measure of engineering stress, but instead of measuring through initial gauge length and initial gauge diameter, if we measure in that way, that means we will take the current value of the diameter and the length, we will get another diagram which is known as a true stress versus true strain based on instantaneous values, and this is what we will get. Okay. So, that means from this point of necking, actually there is an increment in its stress value. Okay, that means this is strain hardening part. Strain hardening part occurs up to rupture point. Okay. But as there is a reduction in diameter, appreciable reduction in diameter, that is why in this region we get this drooping nature. If the observation was made based on the current then diameter, we will get this type of diagram. Okay, that's clear. Okay. And so this is what is shown is how they are related. This is engineering stress strain diagram, this is true stress diagram. Now this is a schematic one. If they are expressed in a particular, for a particular specimen, if they are expressed in the same stress strain scale, how they will change. Okay. So when we measure true strain, okay, the magnitude of true strain at the point of fracture is much higher. Similarly, when we measure true stress, the magnitude of stress is much higher than what we get from engineering stress strain diagram. Okay, this part is clear, right? Now this is known, we are not going to discuss. This is what we have discussed earlier. This is again some deformation. So now the question is why that is important, why stress measure, alternate stress measure, say true stress, true strain, why they are important. They are important from this logic that in our analysis what we do, we carry out some mathematical analysis based on equation of equilibrium in whatever way we express it. But that equation of equilibrium is valid corresponding to which geometry or which phase of the material deformation. Obviously, it is not valid corresponding to the initial geometry or initial phase of the material, is it not? Say this is the initial geometry of the material which is under some loading. If this is the final deformed shape, then of course our equation of equilibrium is valid corresponding to this particular geometry.
Yes.
The same thing is true here also. We are analyzing the deflection of a cantilever. So during the loading operation, okay, it has been, so this is exaggerated, but there will be some deformation, you understand. So there also equation of equilibrium is not measured, or it doesn't follow the initial geometry. This is quite clear.
Yes.
And so that is why this calls for the measure of initial stress and initial strain. But again we observe that this is not the measure, only true stress and true strain, they are not the only measures of stress and strain. There are various other measures of stress and strain. Okay. So let us go into that. What are these measures? Now, this is not what we have discussed up to this point, but you see we have discussed about nominal or engineering stress, which is the force divided by original area, and strain is change in length by original. Now taking constant volume, right? Although there is a question mark, is it valid, whatever. So if there is no change in volume of the material, then obviously this A0 into L0, okay, this is a measure of volume Okay, total volume will always remain constant to this. From here what we get? What is A by A0? This is equal to L0 by L, whatever. So this is what we can also use instead of measuring the length. We can also measure this area, and from there also we can find out the strain. That is one thing. So this is engineering measure or nominal measure. These are the measures following the actual deformed state, which is known as the true state. Force divided by the current area, and strain summation of the instantaneous strain values. So from initial length to final length, we are going on measuring the strain, okay, elementary. And you know that dl by L or dx by x is log n of log n x, okay. So the limit is L0 to Lf. So if we put the limit, it will be ln of Lf minus ln of L0. So this is natural logarithm Lf by F0. So similarly, this A0 by AF is equal to this D0 into df from here, or actually this is, actually this is not area, because what is done here, area is say pi into D0 square, and this is pi into df square. Pi cancels, so we get 2 here. This is what we get from diameter. Okay, so this part is also, this is clear, right? But then let us see something more. So there is a true stress. True stress is force in the current state divided by area in the current stress. This is true stress. And then there is a true strain also. Okay. This true strain is basically 0. Strain is 0 means length is L0, and here this is when our epsilon value is the final epsilon value. Okay. This is length is Lf. If we measure this d epsilon means this one dl by L, we will get the true strain. So this is true strain. As well as there is the conventional strain, change in length by original length. This is the measure through the original or reference area. Okay. Force divided by the original area or the reference area. So now you see in this 1 and 2, true stress is paired with conventional stress. They are mentioned in the same horizontal, in the same box. Right? Here also, the true strain is paired with the engineering stress or say nominal stress. Okay. There is a third row also. So here is another measure of stress and another measure of strain. Right. What is the idea? What are the features of these 3 measures of stress and strain that are coupled together? So the idea is that these combinations of stress and strain, okay, they are energetically conjugate. What does it mean? Because this means to measure energy. Say energy, here it is stored energy inside the material. Okay. So this energy measure would be identical or we will get the actual energy stored in the material if we take these combinations. So, these combinations of stress and strain, they are energetically conjugate there. So, this is true if you in any other area of say mechanics, thermodynamics, whatever. You cannot take any current, any voltage, okay, any pressure, any volume. There are so many measures of those things. You have to take energetically conjugate pairs to measure the energy. This is clear? So, this idea is clear why they are clubbed like this. Now, these two we understand quite easy. What is this thing? The second Parallax stress, what does it mean? You see here, this particular stress, there is a say stress measure, some stress measure. Say this is the true stress as such, okay.
This is true stress.
This S, capital is true stress, and with this we have a strain measure. And with this stress into strain, it is a measure of energy. Per unit volume, and when we multiply this with volume in the reference state, okay, that means the original volume, and this gives us increment of work in the current state. Okay, that way this particular strain, this is how it is defined, and what is this particular strain? This is known as the Green strain or Green Lagrange strain. So, you recall that this is the value we have measured, is it not? In our strain analysis, we had a definition of the nonlinear strain. How that was measured? P star Q star squared minus PQ squared divided by twice into PQ squared. Is it not?
Yes.
So, that is what we measured, Green Lagrange strain. That was the nonlinear relationship between strain and displacement. But the engineering strain and displacement relationship, that was the linear. We have omitted some terms of this Green Lagrange strain and we obtained a linear relationship. Okay, you remember that. So, these are different types of stress and strain measures. And why they are important? Because in actual case, there is change in geometry. So, to express these stress and strain corresponding to this geometry, if we analyze only through this engineering stress and strain, we cannot describe the problem, the true problem. There would be some error in the analysis. That is why we require this alternate measures of stress and strain. So, here this is the thing, this is the relationship between engineering stress and engineering strain. So, this relationship, actually you can follow this one, this is the basic thing. Okay. Some example is also here. So, understand this is a true stress, this is engineering stress, this definition is understood. This is our engineering strain, this also we can measure. From diameter, this is a transverse strain. Okay, this is what we use to measure Poisson's ratio or Poisson's ratio, whatever. But now let us take this thing, okay, and then this true strain is natural logarithm of L by L0, that we have seen, right? So dl by L from L0 to L0, this is 1 by L, so it becomes L at L by L0. Okay, now what is this L by L0? This L is final length, so this is L0 plus delta L. This L, this is L0 plus delta L. What does it mean? This means this is 1 plus delta 0 by L0, and that delta 0 by L0, delta L0 by L0 is this. So this is epsilon engineering strain. So this true strain is natural logarithm of 1 plus engineering strain. So this establishes the logarithm strain and the engineering strain. This clear. And the stress measure is that way direct. Okay, yes. We can find out true stress, and this is what we can find out the true strain if we know what is the engineering strain. That is possible. So these are the relations which we require to find out true stress, true strain. This is what is shown in terms of the cross-sectional area. So whatever, it is the same thing. I have discussed this thing, you see it afterwards, and there are some problems. Okay. So if we measure the change in length, okay, corresponding to in steps, say how the result will change. Engineering strain is always the change in length by original length. Here you see the change in length is 50 to 66 point.
Sorry, so 5 by 50.
This is
the engineering strain is 5 by 50. Change in length.
No, this is 16.55 because 66.55 minus 50. So this is 16.55 by 50. This is engineering strain 0.331. This is the total value. This is not the strain value. This is strain, and this is the point, intermediate point. So for this measure, 50 to 55, what is strain? 55 to 60, that is strain, and again this 60.5 to 60, what is this strain? This is the total. So this is the thing. Right. So we understand how it happens. So now you see what is the relation. This is engineering strain, this is true strain, or actually notation is different. But you see, when conventional strain is, say true strain is 1%, this is 1.72%. Conventional means engineering. But when this is 4%, this particular value is 53.6%. It goes on change. So based on that we have some problems actually. We won't go into these details. Okay. So this is a particular problem where it is required to calculate the reduction in area. This is straightforward, quite straightforward. Only we require the area, which is also given. Initial is 10, final is 6. Okay. Now here true strain is measured from change in area. That was there earlier also. Right? Here in this slide we had
A0 by A.
From this relation you can find out this thing. Now there is an extension of this problem. So here it is slightly different. There is a 12 millimeter initial diameter, gauge length 50 millimeter, and at fracture this is the load. Oh, sorry, at fracture this is 70 kilonewton, 90 kilonewton is the maximum stress, ultimate stress. The minimum dia at fracture, so this 12 millimeter is reduced to 10 millimeter. Right? Determine engineering stress at maximum load, but at that point. True fracture stress, this is true value, not actually. True fracture strain, engineering fracture strain is clearly this 70 divided by the area corresponding to 12. So that is what. Now you would be able to solve this problem, right? Everything is known to you, some mathematical relations are there, you have to put those values. Okay. So these are some of the problems which might come to your, for the purpose of your examination. But you see, this is only the tip of the iceberg, you can say. When you will be solving actual problem like this large deformation problem, it is not that your idea about true stress and true strain would be sufficient. You need to have some idea about that measure of strain, the Lagrangian definition, Eulerian definition, that part we didn't discuss actually in our strain analysis. Okay? So that part is also equally important. So this true stress and true strain, this is just what we are mentioning here. This is just the beginning of an altogether different area where we need to analyze through those large strain, large deformation type of problems. That is, we measured or we mentioned in strain analysis. Recall there was a 2 by 2 box. Our discussion was for linear part only, right? So this much is for true stress, true strain. Okay, we'll stop here today, and next we will be discussing